Hello students, in continuation of our discussion on code acquisition mechanisms and the circuits involved for the spread spectrum communication systems and jamming, we will today go in detail of such kind of the code acquisition mechanism, and we will try to do the performance analysis of these code acquisition circuits, and basically we will try to evaluate the performance in terms of the detection probability and the false alarm probability. Remember, when we are talking about a code synchronization, there are few terms involved related to the performance analysis of a synchronizer, and the performance measure is largely involve the term called detection probability, which basically is telling how many times you are successfully detecting the or achieving the synchronization. I mean, you are detecting the threshold is properly crossing the level, and hence you are declaring that you have acquired the synchronization. If you are detecting, then also it involves how many times you have missed and how many times you have given the false detection. So, falsely detecting something is will be quantified by the probability of the false alarm, and why this false alarm is coming into picture is your whole detection process and the synchronization process is a random process, is a stochastic process involved, because it is a function of it is having a large dependency on the Doppler of the Doppler frequency change or the Doppler derivatives, as well as the different delay profile changes of the wireless communication channel. So, hence the fall, and also some other issues are there, circuit issues are there of the front end RF circuits. Dwell time is the time that we have learned in the previous module, that involves the time for your integration process inside the detection. Apart from all these three, we have a very important parameter called acquisition time. Remember, the acquisition time and dwell time are not the same thing. Dwell time involves the integration time involved inside the detector. Acquisition time is the total time you are taking to declare the synchronization is achieved. See, the dwell time can be having multiple times if it is a multiple dwell time based detector, and at the end the total dwell times that you are taking plus the decision, the time that is involved to apply the verification algorithm, and at the time declaring that the verification, at the end of the verification the synchronization is achieved. This total time is involved inside the acquisition time. As we understand that the detection process itself is a stochastic process, and hence the acquisition time is also a stochastic process, and it's a finally it's a random variable which is having a mean and a variance, and we are really interested to know what is the acquisition time. Basically, the whether our acquisition system is a good or bad, it depends upon several things. One important part is the acquisition time it is taking to converge and declare the synchronization is achieved. Always try to devise the acquisition system which is having the very low acquisition time. It means very fast actually the synchronizer is able to synchronize, and hence you need a very high detection probability to achieve the high acquisition. At the same time, the probability of the false alarm should be very, very low. And this is the ideal situation that we always dream of, and which is the target of designing any synchronizer in practice. And remember one more thing, that whenever we are talking about this acquisition time, and if we see the expression of the acquisition time, later on we will discuss on it. If we see the expression of this acquisition time, we will see it is a function of this PD, the detection probability, the false alarm, as well as the dwell time. So, one may ask like this, that if I know the detection probability and given the false alarm probability, so I can arbitrarily choose the dwell time TD in such a way that I can achieve the mean acquisition time, but the answer is not so easy. If you see the expression of detection probability, Given the false alarm probability and the signal to interference noise ratio at the detected input, you will see that the detection probability itself is a function of this dwell time. So, it is a complicated relation and it is not so easy to pick up comment anything on the acquisition time. Today our task is to develop the expression for this detection probability as well as the false alarm probability. We will try to do the false alarm probability expression, derive the false alarm probability expression first, and to see actually how this relation is coming into picture, and finally, whether we can comment something on the acquisition time. We will consider a system to continue to derive the expression. This is the system, the block diagram of the single dwell time PN acquisition system, and it is a non-coherent detector based. Remember, as discussed in the last module, if it is a non-coherent detector, you will see you do not know anything about the phase ambiguity of the carriers. So, carrier synchronization is not done, and hence you do not have any clue about the phase ambiguity of the carrier frequency, and hence the non-coherent detector is coming into picture, and non-coherent detector involves a band pass filter and a square law envelope detector. Output of the square law envelope detector will be fed into a integrate and dump circuit. It will be sampled, and this parameter that is entering into the threshold device, who is basically a decision device where the verification algorithm is running, he is taking the input of this Z. Remember, this Z, he is the input to the decision device. We will do lot of derivation based on this Z. If the threshold output is saying that the synchronization is achieved, then you are here in this line and there is no feedback going into the local PN code generator. Otherwise, if it is not, synchronization is not achieved, then there will be some correcting information should go inside the PN code generator, and based on this information coming from the decision device, the waveform that is generated inside the PN code, its phase and its timing as well as the phase and timing, it will be changed. Basically, the phase is changed, and in order to reduce the difference of the phase between the received signal PN code as well as the locally generated PN code. So, that is the target, and over the several iterations we believe that actually if the decision algorithm is perfectly running and if it is correct. So, then over the several iteration we will be closely achieving the synchronization at a particular time. So, that is the target, that is the way the whole circuit operates. We will now enter into the signal model. If the signal is present, then remember x t is here in the block diagram. So, that the input of the square law envelope detector, if x t is present, you will receive a signal who is the combination of the intended signal plus the noise. Okay. So, we will start from here in the next slide. So, once my signal is present, my input signal to the square law detector is S t plus N t. S t I can express as square root of 2a cos omega naught t plus psi, and N t is having a cos as well as a sine component, because it is a complex noise getting added, and the omega naught is the carrier frequency in radian, carrier frequency of transmission in radian. A is the RMS value of the RMS signal amplitude, and then psi is actually the related phase of the phase ambiguity related to the transmitted signal as well as added with the noise component. And NCT, NST, they are both the independent band limited low pass zero Gaussian noise processes, and as they are Gaussian noise processes, they are having a variance which is given by N 0 b by 2. What is this N 0? This N 0 is the single sided power spectral density of the noise. Capital B is the bandwidth of the pre-detection band pass filter. Remember, before this square law envelope detector, we had a band pass filter. So, the B, capital B is the bandwidth of this band pass filter here. So, the noise is heavily affected by the bandwidth of this band pass filter. If I substitute this expression by this lower one 1.1, we get 1.1, where this r is nothing but the square root of a plus n c t square plus n s square t, and this theta t is coming because of the tan inverse of this noise component plus the a plus n c t. So, this is the total equation with which we will deal from now onwards, and this is the, remember, this is the signal at the input of the square law detector. So, the output of the square law detector what will be is our next important part to see. Here you transmitted this that we have seen in the last slide, and the output of the square law envelope detector, definitely if the output of the square law detector is written as y t, it will be square of this input, and hence it is finally the square of r square into t basically, and we will be ending up with the expression of 1.3. And it can be easily proved also that this y t will have a non-central chi-square distribution, and it will be having a PDF governed by the non-central chi-square distribution, which this non-central chi-square distribution is written as this, where your I 0 is the Bessel function of the first kind, and gamma is the signal to noise ratio. So, gamma is written as the energy of the signal and divided by the n 0 into b. Remember, we have already seen that sigma square, which is the variance of the noise added, it can be given by n 0 into b by 2. Okay. So, n 0 by 2 is two sided power spectral density of the noise, and b was the bandwidth of the band pass filter who was residing just before your square law detector, and we have just replaced it here, and this is a total expression in terms of the noise variance and the incoming signal we are getting. So, this expression is valid when signal is present. Remember, what will happen if my signal is not present? Means the RMS value of this signal A, which is given by A, that will be now 0. If I substitute the value A is equal to 0 in the upper equation, this non-central chi-square distributed PDF, we will get the PDF of central chi, we will get the PDF of a PDF given by equation 1.6, which is fundamentally the PDF of no signal condition, and it is obtained by substituting A equal to 0 in the equation 1.4, and obviously that it will come to a central chi-square distributed PDF. Remember that where we are right now, let us go back and revisit. We started with the x t, we have squared it, we have entered into the, we have got the expression for y t, and we have tried to see what is the distribution of this y t. We have realized that if the signal is present, it is having a non-central chi-square distribution, and if the signal is not present, it is having a central chi-square distribution PDF. Next part is to enter into the integrate and dump receiver, and remember, in not only the integrate and dump receiver, from y t we will jump here at the point z I. So, not only the integrator is there, integrator and the sampler both are involved in the process. So, here we are taking a assumption that if we understand that capital B is the bandwidth of the signal, because that is the signal band, that was the bandwidth of our band pass signal, band pass filter. So, band pass filter has allowed the signal having a bandwidth of capital B only. If I take the sample at the interval of capital T is equal to now 1 by B. So, this y t which is achieved, achieved at the output of the square law detector, if we now sample it at the rate of capital T, which is nothing but 1 by B, and then those samples, as it is sampled actually following the Nyquist sampling rate, then all the samples will be approximately independent to each other. So, how are you getting the value of this z? So, z is approximately will be given by 1 by the TD is the dwell time that over which you have done the integration, and then you are doing the samples. So, approximately if I take the samples in the sample domain, this expression can be equivalently be written as y of k capital T, where k is varying from 0 to n b minus 1. What is this n b? N b is telling how many number of the samples you can get. The samples approximately that you can get is the what is the sample duration, what is the duration over which you are sampling, it is a tau d divided by the sampling total sampling time. So, fundamentally it is the bandwidth multiplied by this tau d, the dwell time over which you are dealing with. So, fundamentally this N b, capital N b will be large or small or the moderate in number. Based on this, we will see later on that the PDF of the Z can be approximated to some known distribution actually. Otherwise, based on the number of the N b available, we can actually simplify a lot the distribution of the Z, that we will see later on. But currently using the approximation of this 1.7, we can actually revisit the PDFs that we have earlier derived for the signal present and signal not present, and they can be written as like this. And if I utilize actually these two earlier generated PDFs, sorry, if we generate this earlier distributed PDF and if we utilize this approximation, finally we can ending up with the probability distribution of the Z, and which is given by the Pz basically, and Pz will be, this is not y, this will be the probability of this Pz, and the probability of this Z will be given as this. So, it is also a chi-square distribution going on, but it is not not actually having a Bessel function of first kind definitely. And when the signal is absent, if I substitute the A capital A equal to 0, which is equivalently gamma is equal to 0, we will be ending up with the expression here. Now, see here we have a term called Z n b by 2 sigma square, which is basically nothing but normalizing the Z by the term of 2 sigma square by n b as if. So, we will substitute this expression by say Z square, Z star. If I do it, then this expression, both the expression with signal present and signal absent, in both the situation we will be ending up with two more expression given in 1.11 and 1.12. Remember, to avail 1.11 and 1.11 is obtained from 1.9 by substituting Z n b by 2 sigma square by Z star, and 1.12 is obtained from 1.10 by the same substitution. And remember that the first one, I mean 1.11, with this normalization 1.11 is talking about the PDF of the Z, I mean input signal to the decision device when signal is there, signal present, and here signal absent. Now, we are almost actually in the situation where we understand. So, remember, let us go back once more to the block diagram and revisit what we have already understood. We started with a single dwell time PN acquisition system. We understand that it is a non-coherent detector. So, the signal that has entered here at the front end, which was the data signal over which the PN sequence was superimposed. Target is to acquire synchronization between the locally generated PN code and that transmitted PN code, which is superimposed on the data. And as it is a non-coherent detection process, so we are having a band pass filter in the forward path followed by a square law envelope detector, integrate and dump circuit totally, and then a threshold comparator. And over the multiple iteration, the whole circuit is trying to get synchronized with the minimum error sense with the received signal PN code. And we saw that the input to the square law envelope detector, we started with x t is equal to x t is equal to the signal plus the noise contaminated with noise. Square law detector output y t was given as x square t. We saw that the distribution here of y t was in presence of the signal, it gave us a non-central chi-square distribution, and it is largely dependent on the signal to noise ratio. And remember the noise that we have added here in this process here, the bandwidth of this noise is restricted by the bandwidth of the band pass filter presiding the square law detector, which we actually thought to be the capital B. And once this is the, and the noise is having a one sided power spectral density of capital N 0, and hence in presence of the noise, when the signal is present, we see this y t is having as non-central chi-square distribution dependent upon the signal to noise ratio. And if the noise only noise is there, see, that means the signal is absent, then this distribution will look like a central chi-square distribution, substituting the value of the signal section equal to 0, that means the SNR value will be down to 0. Substituting that, we got the both distribution here. Next, we looked into the signal that is entering into the threshold comparator device or the decision device. Here we had an assumption that this sampling is going on at a rate conforming the Nyquist sampling rate, that means at the rate of 1 by capital B, which B was the initial band pass filter bandwidth, and hence now the signal bandwidth or bandwidth of x t, bandwidth of y t, all are limited by B. So, if I go by the capital T is equal to 1 by B, we saw that this can be nicely approximated, and we could also find the probability distribution function of this z when signal is present and signal is not present. So, non-central kind of the chi-square distribution also we find here when the signal is present for z, and central chi-square distribution closely with a different basis function we got with different Bessel function we got for z when signal is absent. So, why we are so interested about the distribution of the signal here is because this is a very important signal part, based on which actually now the decision will go on. What I started with is the performance analysis of code acquisition technique, means you have to define or you have to derive the detection probability and the false alarm probability, right. So, based on this input and its probability distribution, we will now take the decision inside it. So, let us assume that inside the threshold comparator there is a verification algorithm running, where there is a threshold marked as eta. So, the algorithm will tell that where the algorithm will really try to understand how many times the incoming signal, this PDF, is crossing the threshold. And remember, there will be the correct detection if actually for all the cases when this guy, this z I will cross the theta I. So, theta I to infinity, to up to that zone there will be a detection probability going on, and rest of the term actually when the signal is definitely present for the detection probability, correct detection is going on. The same integration will run when the detection, when the incoming signal is falsely crossing this eta when signal is absent. So, probability of false alarm and probability of detection both actually integrate the incoming signal PDF z for the interval that that PDF is crossing eta and reaching from eta to infinity times, that PDF of z is getting integrated. But remember that for probability of false alarm, only difference is that this PDF is in this is a PDF in absence of the signal, and in case of the probability of detection, this integration will run with the PDF that we have obtained when the signal was present. Okay. So, it is a basically substitution of the PDF of the z in presence of the signal and in absence of the signal. Presence of the signal will tell you the detection probability, absence of the signal will tell you the false alarm probability. Now, let us go to the slide where we were. So, here we are, and we with the explanation that I have given with respect to the block diagram. Now, instead of z we have normalized z known as z star. So, we will also normalize the threshold by the same amount 2 sigma square by capital N B, and eta star is given as the normalized threshold. So, the probability of false alarm will be, as I told, it will be the integration of n star to infinity of the probability of z star dz star, where this probability of z star is the probability when the signal is absent, I mean the equation 1.12. And it means that signal is basically not false alarm. Means what? False alarm means the signal is not present, but you are wrongly detecting that the signal is present. So, given this probability distribution, how many times actually you are detecting the signal is present when signal is really not present is the question. And as integrating up to infinity is a tough task, so we will change the integration as 1 minus 0 to eta star, and if you compute it right at home, if I compute it, we will be ending up with the expression like 1.13, where the probability of false alarm will be exponentially given by exponential of eta star with the multiplied with the summation of k to 0 to n b minus 1 n star to the power k by factorial k. So, it is the exponential expansion of this guy who is coming into this pattern, and with that we will try to end up the probability of this module. We will try to end up this module with the understanding of the probability of false alarm. Our next important understanding will be to derive the expression by the probability of derive the expression for the probability of detection in the next